You know that specific kind of panic at the end of a group dinner?
Oh, yeah. The waiter drops the check.
Right, the waiter drops the check, and suddenly everyone at the table turns into a forensic accountant.
It is the ultimate social dampener.
It really is. You've got, one person saying, well, I didn't have any wine, and another saying, I only ate half the appetizer.
And someone else is frantically trying to do long division on a napkin.
Exactly. It's
Yeah.
total chaos. And usually we just solve this by saying, hey, someone just pay it and we'll Venmo you,
But then you have to actually remember who owes what.
which is exactly where apps like Splitwise come in and basically save friendships. But I've got to be honest with you right off the bat.
Yeah.
When I first looked at our source material for this deep dive, this
Hmm.
really comprehensive low-level design walkthrough by Rune Daher, I got a little skeptical.
Skeptical. How so?
Well, I mean, we're talking about dividing a bill here. It's third grade math. Do we really need UML diagrams and design patterns and a 45-minute architectural breakdown for an app that basically just does, total divided by n?
See, that's the trap. That is exactly the trap. If it were just you and me splitting a pepperoni pizza down the middle, sure, total divided by 2 works perfectly fine.
Right.
But the second you add a third person or partial payments or, and this is the big one, existing debt from yesterday's lunch,
Oh, right.
that simple third grade math turns into a literal graph theory nightmare.
Okay, graph theory nightmare definitely got my attention.
Because we aren't just building a calculator today. We are building a system that has to manage state, consistency, and debt relationships between multiple nodes. And those nodes are human beings.
Which makes it messy.
Very. And that's why Munmai's walkthrough is so great. She takes us from the rough whiteboard drawing all the way down to the actual Java code. It really bridges that gap between, I have an idea for an app, and here is how I structure the classes so the code doesn't turn into a giant bowl of spaghetti.
So that is our mission for you today. We are going to architect Splitwise.
Yeah.
We need to figure out how to take that really messy dinner bill and turn it into clean, object-oriented code.
We're going to identify the basic objects, implement some pretty heavy-hitting design patterns.
Like strategy in Singleton, right?
Exactly. And finally, we'll crack the core algorithm that actually calculates who owes who. And just a quick note for you listening, while this is a famously classic coding interview question, this isn't just for people prepping for a job at Amazon or Google.
No, not at all.
This is really about learning how to think bottom up. It's about building small, reliable components that just click together to handle really complex logic.
Right. So let's unpack this. If I'm Runmai, or honestly any engineer just staring at a blank screen,
Yeah.
where do I even start?
You start with what she calls the rough flow. Because before you write a single line of code, you have to visualize what the user actually sees and what they do.
Okay, simple enough. I open the app. I see a dashboard.
Right. The dashboard is your central hub. It shows your friends and your total balance.
Okay.
But to even have a dashboard, you need the fundamental building blocks. You need friends and you need groups.
Which makes total sense because I might split a bill with just one friend, or I might have a massive trip to Cabo group with like 12 people.
Exactly. But the absolute star of the show, the thing that drives this entire system, is the expense.
The expense. Now, in my head, an expense is just a number. It's $50,
But it's not.
right? In the source,
Yeah.
Runmai breaks this down, and it clearly carries a lot more baggage than just a price tag.
Oh, it has to. Think about the data attributes. An expense needs a description, obviously. It needs an amount. But crucially, it needs a paid by user, the actual person who swiped their credit card.
Right.
And then the most complex part of all, the split type.
And this is really where the complexity starts to creep in, isn't it? Because splitting isn't always 50-50.
Far from it. The source identifies several really distinct ways we might want to split that bill. There's equally, which is the default everyone knows.
Sure.
But then there's exact amount, where maybe I say, hey, I'm paying 20, you pay 30.
Or percentage.
Percentage is super tricky, though, because unlike equal splits where the system just does the math for you, percentage splits rely entirely on user input, and that input has to be perfect.
Oh, I see. Because you can't have a bill split 40%, and I don't know, 10%.
Exactly. Who pays the other 10%? The restaurant.
Right. The math doesn't math.
So the code needs validations. This is a massive point in the low-level design. If a user chooses percentage split, the code must ensure those numbers sum up to exactly 100%.
Makes sense.
If you choose exact amount, the individual shares have to perfectly equal the total bill. If it doesn't match up, The code has to reject the request immediately.
Okay, so we've got the rough idea mapped out. We have users, we have groups, and we have these complex expenses with all these different rules attached. Now, Rune might suggest using a bottom-up approach to actually build this thing. What does that look like practically?
It means we don't start by trying to write the massive, complex algorithm that settles all the debts.
We don't start at the top.
No, we start by defining the smallest, most basic Lego bricks of the system, the objects that just hold our data. Once those are rock solid, then we build the logic on top of them.
Okay, let's build some Legos. We already mentioned the expense object.
Yes. So in the code, the expense object holds the ID, the description, the amount, the paid by user, and the split type. But it also holds a list of something called split details.
Split details, and that's just a list of names, like who is involved.
A bit more than that, it's a list of split objects. A split is this tiny atomic class that just links a specific user to a specific amount owed.
Oh, I see.
It's the absolute fundamental unit of debt. Bob owes $15. That is one split object.
Got it. Now, for the split type itself, equal, percentage, all those, the source mentions using an enum.
Right, the expense split type enum.
For those who might not know, what is that doing for us?
In Java and most languages, an enum is just a fixed set of constants. So we define equal, unequal percentage. This allows the rest of our code to easily categorize what kind of math operation we're about to do without relying on messy text strings that someone could misspell.
Okay, so we have the bill, which is the expense. We have the slice of the bill, which is the split, and the category, the enum. Now we need the actual people, the user.
Right, and the user object has all the standard stuff you'd expect, user ID, name, email, but it has one specific field that is absolutely critical to this whole operation.
What's that?
It's called the user expense balance sheet.
User expense balance sheet. That sounds intense. What's that actually doing here?
Think of it as the brain of the user's financial state. But here's the really interesting architectural choice. Mumbai implements this as a map. Specifically, a map where the key is another user and the value is a balance.
Okay, let's pause right there. Why a map? Why not just use a simple list of all my transactions?
Speed.
Speed?
Pure speed. Think about it. If you have a list of 500 past transactions, and you open the app and want to know exactly how much you owe your friend Bob,
I'd have to scan the whole list.
exactly. The code would have to scan through that entire list, line by line, adding and subtracting every single time Bob's name appears. That is slow.
Right, that's O of N complexity for the nerdy friends out there listening.
Which we want to avoid. By using a map, we get O of 1 lookup time. Constant time.
Wow.
We just ask the map, hey, get me the balance for Bob, and it returns the final answer instantly. It literally does not matter if you have 10 transactions or 10 million transactions. The retrieval speed is exactly the same.
That makes total sense. So this user expense balance sheet tracks exactly where I stand with every single friend individually at all times.
Precisely. And it tracks 4 specific metrics per friend. Total your expense, which is what you actually paid, total you owe, which are your debts, total you get back, your receivables, and total payment. It is basically a personalized mini ledger for every single relationship you have.
Okay, so we've got our core objects. We've got highly efficient data structures. Now comes the part that I really think separates just a coder from a true software engineer.
The patterns.
The patterns. We have these different split types, equal percentage, exact. Now, I'm going to play devil's advocate here.
Go for it.
Why don't we just write a function? Just a big switch statement or a chain of if-else blocks. If type is equal, divide by n. If type is percentage, multiply by x. It would be like 5 lines of code. Why are we overcomplicating it?
We aren't overcomplicating it, we are protecting it, and it comes down to the open-closed principle.
Okay, let's unpack that for everyone.
Imagine you do write that giant if-else function, and it works great. You deploy it. But next week, the product manager comes to your desk and says, hey, we want to add a brand new feature, split by shares.
Okay, so I just go back into my function and add another else if block at the bottom.
And that is exactly the problem. You are modifying a core, tested, already working piece of code. Every single time you open up that function to add a new split type, you risk accidentally breaking the logic for equal or percentage.
Oh, I see. You could introduce a bug into something that was completely fine yesterday.
Exactly. You are opening up the code to bugs. The open-close principle states that your code should be open for extension, meaning you can add new features, but closed for modification, meaning you don't touch the old stuff.
So you want a system where you can add new features without ever opening the files of the old code.
Yes, and that is exactly why Mrunmayee uses the strategy design pattern here.
The strategy pattern.
She creates an interface, which is basically a strict contract called expense split strategy. And this contract basically says to the code, look, I don't care how you calculate yourself or how you validate yourself, but you must have a method called validate split request.
So something like percentage split becomes its own entirely standalone class.
Yes. Percentage expense split is its own class, and it checks if the inputs sum to 100. Unequal expense split is its own class, and it checks if the amounts equal the total.
That is brilliant.
It is, because if that product manager comes back and wants to add split by shares later, you just create one brand new class. You never touch the existing working code.
That is so much cleaner. It's almost like having a different dedicated specialist for each type of job, and the app just hands the paperwork to the right specialist without trying to micromanage how they do their job.
That's a really great analogy, actually. It keeps the core flow of the application completely decoupled from the specific nitty-gritty math of the splits.
Now, there's one more design pattern mentioned in the source material. It's usually the very first one people learn in computer science.
Yeah.
The singleton pattern. Where does that fit into Splitwise?
The singleton is used for the absolute main class, the Splitwise class itself, the main driver of the application.
Okay.
The rule here is that there should only ever be one single instance of the Splitwise application running in the system.
Why is that?
Because you don't want two different versions of the app running simultaneously, both trying to update the exact same database records at the exact same time.
Oh, that would be total chaos. Balances would be overriding each other.
Exactly. So, to prevent that, the constructor of the class is made private, and there's a static method called getInstance that returns the one true single instance of the app. This main class then manages all the top-level controllers.
Which brings us perfectly to the managers. The controllers. Now, for the non-technical listeners joining us in this deep dive, the word controller can sound a little bit vague. What are they actually doing?
Think of controllers as the traffic cops of your software.
Traffic cops.
Yeah. They sit right between the user, the UI you tap on, and the data, those back-end objects we just built. They take the user's request, figure out who needs to handle it, and direct the traffic.
And the source outlines three main ones: user controller, group controller, and the big one, expense controller.
Right. User controller and group controller are pretty standard. They handle adding users to a list or creating groups and putting members in them. Simple stuff.
But expense controller is the heavy lifter.
Expense controller is where the magic happens. When you hit save on a new dinner bill, the expense controller executes a very specific three-step dance.
Walk us through those three steps.
First, it looks at your input and selects the correct split strategy. So it grabs that equal or percentage specialist we talked about.
Okay, step one is routing.
Second, it immediately calls that strategy's validation method. It asks, hey, do these percentages actually add up to 100?
And if they don't, what happened?
It throws an exception and stops everything right there. The user gets an error message. Absolutely no bad data is allowed to enter the system.
Love it.
But if it does validate perfectly, it moves to step 3. It finally creates the actual expense object in the database, and then it calls the balance sheet controller.
Okay, this is the grand finale, the balance sheet controller. This is the algorithm that actually moves the money. Well, virtually at least.
It is, and it's incredibly logical if we just step through it carefully.
Let's do exactly that. Let's turn this into a live simulation for you listening. We have 3 friends, Alice, Bob, and Charlie. They go to a nice dinner. The bill comes out to $3,000.
Yeah.
Alice puts her card down and pays the whole thing. Walk us through what the code actually does the moment she hits save.
Okay, let's trace it. Step 1, identify the payer. That's Alice. The system goes and grabs Alice's balance sheet, that super fast map we talked about earlier, and it updates her total expense metric to $3,000.
Got it. So Alice is technically out $3,000.
Right, she paid the restaurant. Now, step 2, the loop. The system has to iterate through the list of all the people involved in this specific split. So the list is Alice, Bob, and Charlie.
Okay, so it looks at Alice first, since she's on the list.
Right, but it does a self-check first. It asks, is the person currently in the loop the same person who paid? The answer is yes, it's Alice. And Alice obviously doesn't owe herself money.
Right.
So the system just skips her.
It moves to Bob.
Correct.
Yeah.
Now let's assume they agreed to an equal split. So the math says Bob owes $1,000. Now, a junior naive engineer might just write a line of code that says Bob owes $1,000 and call it a day.
Right.
But what if Alice already owed Bob $500 from lunch yesterday?
Oh, Right, because you don't want Bob to Venmo Alice $1,000 today, and then Alice to Venmo Bob $500 tomorrow. That's super inefficient.
Exactly. And this is the crucial step in the algorithm. Check previous balances. Before writing any new debt, the system checks that O of 1 map. It says, is there existing debt here?
And finds the 500.
Yes, so it nets it out automatically. If Alice owed Bob 500, the system cancels that out against the new dinner. Now Bob only owes Alice 500.
That is so smart. It minimizes the actual transaction automatically.
It does. And then once that math is perfectly netted out, it performs a double update.
A double update.
It updates Alice's sheet to say get back 500 from Bob, and then it instantly switches to Bob's sheet to say owe 500 to Alice.
So for every single transaction, the system is strictly updating two completely separate sheets. The person who paid and the person who didn't.
Yes, it's classic double entry bookkeeping, just adapted for an app. It ensures that if you look at Alice's phone screen, she sees Baba owes you. And if you look at Bob's phone screen, he sees you owe Alice. The state is perfectly consistent across both users' devices.
That is just really satisfying. It takes all that social awkwardness of asking for money and turns it into this rigorous mathematical loop of checks and balances.
And that is the beauty of a good low-level design. By actively separating the validation logic, which is the strategy pattern, from the storage logic, the balance sheet map, from the flow logic, the controllers, you end up with a system that is incredibly robust.
Now, before we wrap up this deep dive, I do want to touch on something the source mentioned right at the end as the sort of follow-up interview question. We just talked about netting debt between two people, Alice and Bob. But what about the triangle?
Ah, yes. The graph problem.
Right. Because if Alice owes Bob $20 and Bob owes Charlie $20 and Charlie owes Alice $20, technically nobody should have to actually pay anyone anything, right? The money is just moving in a circle.
Exactly. And if your code doesn't actively solve for this, you have money flying around the internet completely unnecessarily. The source brings up something called the minimum cash flow algorithm as the solution here.
How does that actually work under the hood?
It basically stops treating users as just individual people with individual receipts, and it starts treating them as nodes in a directed graph.
Okay.
It calculates the absolute net flow for every single person. It asks, are you a net creditor, meaning overall you are positive, or are you a net debtor, overall negative?
So instead of looking at individual IOUs between friends, it just looks at the big global picture of your finances.
Yes. And then it tries to match the biggest debtor in the entire group directly to the biggest creditor. It completely bypasses the middleman.
Wow.
So instead of person A paying person B and then person B taking that money and paying person C, the algorithm calculates it and just says, hey, person A, just pay person C directly and we'll call it even.
Wait, that is the Simplify Debt button in the app.
It is. That's exactly what happens when you toggle that feature. It's mathematically optimizing your friendships, essentially. Less money changing hands, fewer bank transfers, fewer arguments.
That's incredible. And real quick, just one more follow-up from the source. What about scale? Because all of this works beautifully for us three at dinner, but what about Splitwise having millions of active users?
Yeah, that's where low-level design kind of hands the baton over to system design. You simply cannot recalculate the entire history of every single transaction every time someone opens the app. The database would literally melt. So the source suggests introducing caching. You store the current finalized balance state in a super fast cache, and you only update the database based on the new deltas, the new changes coming in.
Makes total sense. Well, I have to say, I will absolutely never look at that split button the exact same way again.
It's a lot of hidden machinery.
It really is. It's not just dividing by 3. It's instantiating a strategy pattern. It's validating against an enum contract. It's updating a hash map with O of 1 complexity. And it's running a background graph theory problem to save me from making 2 Venmo transfers.
When you list it all out like that, it sounds exhausting, but it works.
It works beautifully. And I think the big takeaway for you listening is that even the most everyday casual tools we use on our phones are built on these massive fundamental computer science concepts. Next time you're coding, even if it's just a small personal project, try to think about that bottom-up approach. Build your Legos first.
And don't be afraid to use design patterns. I know they can feel abstract, but they aren't just for textbooks. They are literal tools designed to keep your future self from hating your past self's code.
Wise words. And it leaves me with a really interesting thought. We spend so much time talking about how apps make our lives easier,
Yeah.
but we rarely think about how every digital convenience we have is masking this massive, invisible web of computational labor.
Absolutely.
It fundamentally changes human trust. We don't have to trust each other's math anymore. We just trust the algorithm. Something to mull over the next time you're out to eat. Well, that wraps up our deep dive into architecting Splitwise. Hopefully, your next group dinner bill feels a little less chaotic, or at the very least, now you can explain the graph theory behind it while your friends roll their eyes at you.
Please don't actually do that at dinner.
Thanks for joining us on this deep dive, everyone. Catch you next time.